In our previous video, we were talking about how the concentrations of hydronium and hydroxide are related, and we have seen an example in which we dissolve a strong acid in solution, and that strong acid changes both the hydronium concentration and the hydroxide concentration, because these two substances are connected through this equilibrium and through an equilibrium constant. Now let's do the same case as last video, but now we're going to calculate the concentrations of hydroxide and hydronium when we externally add 0.1 molar of strong base. If we have 0.1 molar of strong base, it means that we are literally adding 0.1 molar of hydroxide. So the hydronium will still be 10 to the negative 7 for pure water, and to the hydroxide that in pure water was 10 to the negative 7, we need to add the 0.1 molar that we have added because of the strong base. We're going to assume that this is pretty much just 0.1 molar, which it is. If we're adding products by equilibrium Le Chatelier, it means that the reaction will displace towards reactants. So we're going to remove a certain amount, let's call it X, for both products. Initial minus the number of change, it's this much and this much, so the Kw, which is 10 to the negative 14, is 10 to the negative 7 negative X times 0.1 minus X. If we solve for X, you will see this value, and the concentration of H3O plus is 10 to the negative 7 minus X. If you substitute this X in here, what you obtain is that H3O plus, or hydronium, is 10 to the negative 13 molar. Even though we have added a base, we see a change in the concentration of the hydronium ion, because hydronium and hydroxide are connected through the equilibrium of water. So let's do that faster without the ice table, in which we're going to assume this, that we are not going to assume that there's already a 10 to the negative 7, because those numbers are so small. We can just do it much faster, and you'll see how we save some time. So again, what are the concentrations of hydroxide and hydronium if we add a strong base that is 10 to the negative 3 molar? So your base is 10 to the negative 3 molar. So this means that, and you would say, no, but there was a little bit of, because of the neutral water there was this, but compared to the 10 to the negative 3, this is 4 orders of magnitude much larger, so I'm going to assume that it's just that. Likewise, to calculate the hydronium, I do not need to set up the ice table, because I'm just interested in the final result. So 10 to the negative 14 divided by 10 to the negative 3, this is going to be 10 to the negative 11 molar. Okay, so we figured out the concentrations of hydronium and hydroxide without having to calculate any ice table or solving any quadratic equation. It's much easier. So let's see what we have learned. What are the ranges of concentration for an acidic solution? So we said that for a neutral solution, the concentration of OH minus is the same as the concentration of H3O plus, and that's 10 to the negative 7 molar. Notice that when it's acid, your H3O plus has to be more than when it's neutral, because you have added some acid. So it has to be more than the pure water. We have added some acid, that's why it's an acidic solution. If we have added some acid, it means that the concentration of H3O plus has to be larger, and therefore if this one increases, OH negative has to decrease, so that the product of them is still 10 to the negative 14. So this is the range for H3O plus and OH negative for an acidic solution. Likewise, what are the ranges for a basic solution? Well, if it's basic, it means we are adding OH negative. That means the concentration of OH negative has to be larger than what there was already there because of the neutral pure water. And if OH negative is increasing because we have added, it means that H3O plus, let me write it here again, H3O plus If one is increasing, the other one has to be decreasing, so that the whole thing is 10 to the negative 14, which is the value of the equilibrium constant. So in this case, if the hydroxide ion is increasing, the hydroxide ion is increasing, the hydronium has to be decreasing. Okay, so that this is smaller than 10 to the negative 7. So these are the criteria for a basic solution. Hopefully that makes some sense. We will apply this criteria to many other problems.